Thank you very much. We have a very cozy room here today, same as yesterday, so feel free to interrupt at any point. This is a super short presentation about some of the additions in the Linux kernel 6.0. And of course, I don't really like to spend my time on less than 10x performance improvements. So hopefully your expectations are not too high at this point. Linus Torvalds, the benevolent dictator of our beloved Linux ecosystem, has a bunch of amazing quotes. Some of them I strongly disagree with, like, I hope AVX 512 dies a painful death. Strongly disagree. I think maybe one of the best, in many ways, instruction sets that we have today. The other one is less related to tech, I guess, or maybe even more. Software is like sex. It's better when it's free. But then he also has a few opinions on databases. And one of the opinions that he likes to express is database code is tasteless and slow. He has a bunch of quotes on this topic. Sadly, I don't have a meme right here on the slide to put it here. But he has a point there. So when we look at the hardware systems that are available today, we get machines with 100+ cores. Many of them come with AVX 512 support or ARM-SVE. ARM-SVE has been around. The scalable vector extensions has been on both Graviton 3 and Graviton 4. Hardly any piece of popular software uses them. DDR5 is broadly available, so we can get 400 gigabytes per second worth of throughput on a single socket. HBM3, which comes on many of the GPUs, allows us for 3 terabytes per second of throughput, and you can access it not only in matrix multiplications, but also all kinds of database logic, like reductions and that kind of stuff that happens in all-up workloads. But the stuff that we discussed today is more related to OLTP, so more transactional workloads and small packet processing. And for that, for those small packets, the networking cards are just as fast, 300 gigabits per second, 400 gigabits per second, practical versus theoretical throughputs that you can get. And things don't really stop there. So a couple of years ago, I was writing a blog post about the hardware purchasing supercycles, what we were about to expect from the next wave of data center purchases. And one of those technologies was CXL, which is a cache coherency protocol for memory extensions, and practically adds a new entire category of PCIe devices that we can mount into our servers in a somewhat different way. A good example, or like the canonical example of this, not related to the canonical company, is having PCIe cards with RAM. So instead of just pushing pushing RAM into DIMM slots, you can instead mount it into PCIe slots, and there's a very complicated machinery that makes sure that memory fragmented between so many different systems with different latency and definitely different throughput stays coherent with each other. So surely there must be a lot of stuff happening in the kernel that allows for this kind of technology, some of which is like truly complicated, and we will not go into details. Like there are many, many ways to do I/O on modern systems, and I use I/O generously. So I/O, or input-output, is anything separate from the CPU itself. So we can even think about like RAM access as I/O. For I/O, there are many different interfaces. The most conventional, best-known one is the POSIX interface with pread and prewrite blocking synchronous system calls. There are other technologies that are relevant to understand about the kernel bypass, like memory mapping powered by the underlying I/O MMU, memory mapping unit, which is a hardware piece. We'll not talk about mmap. I think everyone here is familiar with it. But then around early 2000s, Linux actually got its first asynchronous interface, which is AIO. It's surprisingly old, so it's, if I'm not mistaken, it's over 20 years old now. Still, it's not very broadly used, but it already allows us to build systems that do I/O asynchronously. So you dispatch an operation, you go do something else, and then when I/O is ready, you fetch it still it was a system call. And in mid-2010s, maybe closer to the late 2010s, I think it's fair to say that Jens Oxbow personally started a project called IO-Uring, which was an extension of the default I/O mechanisms to support asynchronous non-blocking I/O. What it means is that you allocate memory that is shared between user space and kernel space. So you practically memory map anonymous pages, you share them between your process and the kernel process, and you submit into that memory, as if it's a queue, operations that will be fetched by the kernel and propagated down to the driver. You can actually even avoid that step altogether. So there are technologies that allow you to go further and do entirely user space I/O, like SPDK and DPDK. A huge part of their support is practically done by Intel engineers and previously Micron. Now those projects are not as popular. And deploying SPDK and DPDK in the cloud is a nightmare on which I've spent a couple of my years. What is much more feasible is just using IO-Uring, because it comes standards on the Linux kernel. And starting with Linux kernels 5.1 or 5.4, I think a lot of the operations that are already practical for both networking and storage have been supported. But the question here is what's new in 6.0 in the last 2 years. So before we get to like the actual system calls, or like actually opcodes for IO-Uring and the new operations, I just want to remind you how expensive it is to perform a system call. So just calling a function in native compiled code is a question of a couple of nanoseconds. Practically a lifetime by computer standards is maybe like 5 cycles or 10 cycles, depending on what exactly you're doing and on which architecture. If you are fetching something like get PID, which is the process ID, if it's cached within libc, the operation will of course be very fast. But if we go to real system calls like the preads and pewrites of the world, we can easily end up spending multiple microseconds on each call. And microseconds is actually a lot of time. It can be thousands or close to like 10,000 CPU cycles. In 10,000 CPU cycles on a modern CPU, if you utilize 4 ports and you use SIMD instructions, you can perform hundreds of thousands, maybe a million scalar operations. So the cost of writing or reading 1 byte is equivalent for you to performing a million number crunching operations. So you probably would want to avoid those system calls. And one of the things that we've been doing, we've been trying to evaluate how this would affect the whole vertical. So with some of my teams, we've built a set of database engines that we haven't yet open sourced. This is like one of the few pieces that's still on the radar for the next couple of years. Implementing key value stores in persistent memory with full kernel bypass. And the outcome of this is that you can go against Facebook's RocksDB, which is probably world's most important and popular persistent key value store, powering half of modern database companies, and beat it in every single workload by a factor of 5 to 10, easy peasy, maybe more. The way this works is IO-Uring, as it may stand from the name, allocates those ring-like structures in shared memory. As soon as you submit your operation, you can actually like force the kernel to take over, take some of those operations, propagate it down into almost identical queues on the driver side, and then atomically different indicators will let you know that this operation has been completed or it hasn't. Those are some practical numbers from what we've measured on our own cluster with our own SSDs. So if you get enterprise-grade NVMe devices today, if you perform synchronous I/O on a single SSD, you can achieve 100,000 operations per second. 100,000 operations per second may already sound a lot if you're a Postgres user, because like most databases that companies use today are many, many, many orders of magnitude slower than the hardware permits. And you can go asset transactional with 30 million transactions per second on modern hardware. It's just that software is mostly legacy these days. But still, okay, 100,000 operations per second if you do blocking synchronous I/O. Then, if you switch to AIO, which is the 20-year-old Linux interface, on that drive, you can achieve 250,000 operations per second. That may sound like a lot, but when you buy the SSD and you take a look at its data sheet of branding materials, you'll see a number that is probably higher than this. So if you go for enterprise-grade hardware, it will say something like 1.5 million operations per second. And I don't know too many databases that do 1.5 million operations per second, even though many of the servers have a lot more than a single SSD. The servers that we use have 24. So probably we can go better. Kernel bypass with IO allowed us 3 years ago to get to 900,000 operations per second, which still wasn't the limit for hardware even back then. And user space drivers rewritten entirely, like with our assembly level tricks, got us to 1.2 million operations per second. Still, assuming the complexity of going to like full user space, IO is a great balance of performance. So at some point, I thought, why not do the same for networking? And this resulted in this Hacker News blog post, which was my weekend rant on how slow the networking libraries are these days. So we trained a bunch of models for AI, and we open sourced them under Apache 2 license. And people started deploying them on IoT devices, and so did we. And we got the inference time of multimodal perception models across 20 languages down to 0.5 milliseconds. So you can run 2,000 batch size 1 inference cycles on a consumer-grade hardware 2,000 times per second for AI. And then you take the networking library, which only is supposed to take bytes from one place and put them somewhere else. And even without encryption, the numbers that I was getting was like 3,000 RPS. So like I was realizing that I'm going to lose a lot of performance serving my models with like existing libraries. So I tried rewriting some of the networking with kernel bypass as well. And the result was that I got from 3,000 RPS to 230,000 RPS. And I got the latency from 1.2 milliseconds on Graviton 3 instances down to 22 microseconds. Not too bad. Sadly, it hasn't yet become a standard practice, and Jens, who's the author of IO has been posting a lot recently that he really wants 2025 to become the year of kernel bypass for networking, as do I. So what are the new cool things? Kernel 6.8 is broadly available. The long-term support version of Ubuntu, the most recent one, comes with that specific kernel version. Though if you want to be at the bleeding edge, you probably should upgrade to 6.11. If you're in the cloud, it's not as easy because like the system calls will just still be transparently synced down to the host image. But if you're running on your local machine, there's actually a point in upgrading from LTS to a newer version if you want to do kernel bypass stuff. In 6.11, we got a feature called bundling. So you can put multiple operations like sends and receives together. And there are many, many ways on how you can place the IOVX. Those are like the small structures describing continuous spans of memory that the driver has to propagate down to the, the operating system needs to propagate down to the driver. Another cool feature is that there is now zero copy support, especially for the send operations. And that works for most packets under 3,000 bytes. And if you remember the constraints of the TCP/IP stack, you will realize that 3,000 bytes is actually a lot. Most messages will be separated into smaller chunks than that. So for TCP/IP, in absolute majority of cases, your maximum transmission unit would be of the order of 1,050 or 1,040 bytes, if I'm not mistaken. So zero copy supported, but you may need some other settings in your operating system environment to be configured appropriately. And another nifty, nice feature, but very important for practical implementations is absolute timeouts. So when you implement a proper networking library, almost always you need to have like some fail-safe to tell the system what to do if the operation takes too long. Maybe you're not getting the response in time. And for this, the absolute timeouts are absolutely amazing. To give you a vision of what this looks like, the IO calls are fairly simple. The documentation is somewhat divergent. So there are the man pages, but I think the ground source of truth is still the liburing GitHub repository. And maybe like one last but not the least thing is reusing buffers, which is relevant for both storage, but also potentially networking one day. A lot of the operations in this user space bypass things operate on registers that you have to pre-register between the kernel space and the user space. If you work on systems that have like a terabyte of RAM, which is my default setup, then even addressing a terabyte of RAM is like a second or two, and just like propagating this like range of addresses is really hard and slow. Sadly, most of the software is kind of lazy in terms of allocating threads all the time. So like you have a new client or user or whatever, and you allocate a new thread for that user. If you just do this with IO-Uring and other kernel bypass tricks, you will end up waiting for another second for every thread to spin up just because the buffers have to be remapped for this new thread. 612 feature IO-Uring cloning buffers helps you with that. And maybe last but not the least is KTLS support, which I think is still a miracle, and I don't believe it exists, which allows you to offload some of the transport layer security to the Linux kernel. I've never got it to work properly, so I'll just leave it as advertising material. Don't trust it until you know this works. CXL would require a lot more work for us to get going, and it's not directly related to Linux kernel, but it's part of the same ecosystem. And in our case, we ended up writing a ton of code, some of which we've already open sourced under those projects. So if you want to dive deeper into like how all of this works, feel free to reach out, fork, and contribute. Thank you.